Next speaker is Arjen Vine from AM6, and he's part of the actual formal program, so we're going to accord him more time, obviously.
Let's a little into it. All right. When AM6 started actually in 1993 as a humble coax cable, which coincidentally multiple routers were connected to, and the people operating these routers figured out, hey, we can talk to each other on this cable. And yeah, that got more popular and more popular, and that cable got replaced by two Cisco 5500 switches. That was basically AM6 version 1. Then around 2000 it was changed by some foundry network switches to support gigabit. That was version 2. And some technical stuff amongst myself came along, and we built AM6 version 3. And that is where this story starts. I'm first starting with some overview of what AM6 version 3 was, then what our new platform is, how we migrated to that, and I want to share some operational experience with this new great platform. So around June 2009, we were still running on AM6 version 3, and it looked like this. 6 sites, 2 of the sites had core switches in the middle, and we basically had a red network and a blue network. It are 2-star networks. These 2-star networks were also accomplished below with some older big iron 15000s and some RX switches. The 10 gig E's were done with MLX and MLX 16 MLX 32 switches. They were connected via so-called PXCs, that are layer 1 switches. And we used, very importantly, Brocade's port security feature to prevent disasters happening if people made loops. Basically, as I said, AM6 version 3 were 2 separate networks. One network was active, the other one was on standby and not carrying any frames once it was standby. And we had on an external box, we had a piece of software we developed ourselves called Photonic Switch Control Daemon, which controlled the layer 1 switches. This is very briefly how that worked. On the left side, you see the red network active, and the photonic switch basically disconnected the router on top from the blue network and connects it to the red network. If we detect somehow some problem, the whole thing switches over to the blue network. How does this whole thing talk to each other? Well, it uses the proprietary protocol VSRP, and basically that is how Foundry designed it. This network had some scaling problems in the end. Up to now, up till AM6 version 3, we were always able to buy bigger boxes, to put in thicker backbone links, to aggregate multiple 10 gig usage. And from all this experience, we developed a sort of model on how the port growth will be. And we figured out, like in the summer of 2009, we'll run out of our current platform, and there was absolutely no sign that there would be a bigger switch available. All the vendors said, no, we won't have a bigger switch for you. Some vendors have a marginal bigger switch, but not something that could help us. So we had to rethink. We had to look at all the problems in AM6 version 3. Well, the first thing is, as I said, we run out of ports. The switches were full. We had these big MLX 32 switches with 128 10 gig ports, and they were completely fully utilized. We could not go any much further on this platform. Besides that, the
the redundancy or the problem restoration I just described with swapping over from one network that is active to an inactive network that should then be active has its problems as well. First of all, you don't know where you switch to. It might be that the inactive network died without telling you. So, yeah, this became more and more a problem as more and more members connected to the, with 10 gig and were connected to the photonic switches. And yeah, we needed to do something. So we started to think about a total new network. And the requirements were that we, at least in the core, we needed a double amount of ports. And we needed to do that by putting switches in parallel, which is something you cannot do with plain Ethernet. It will create a massive loop. That won't work. On the other hand, we would like to keep the resilience by having this photonic switch where we connect members to, so we can take out a complete switch if we need it. We can switch it out, put people on another switch, and work on the switch we switched out. That helped us a great deal over the years we were running on version 3. Yeah, another thing is it would be nice to have larger switches where customers connect to, so we have more local switching, which means that we can have thinner backbone links. And also, as I described earlier, we had these MLX32s, we had RX16s, we had jet core, big iron jet cores. Basically, we had the whole product gamma of Foundry in our shop, and you need all these spare parts. You need all the different software versions, which you need to test in your lab. That gives a sort of management overhead. So, yeah, we would like to go to a single platform if possible. And it would also be nice if it would be sort of future-proof, that we could put in higher port densities once they come available, also 100 gig Ethernet interfaces. So, yeah, we came up sort of with a picture like this. In the middle, you don't see 2 core switches, but 4 core switches. And instead of 2 different networks, the networks are all meshed together. So all the Ethernet switches you see are connected, have a link to every core switch. So each Ethernet switch has a minimum of 4 links towards the core switches. Still on top, we have the photonic cross connects, the layer 1 switches, where we connect our members to on 10 gigabit. So we would still be able to have redundancy in terms of complete switches that we can switch out and switch in our network. Parallelization, we came out that we need to go to MPLS, VPLS, because that would allow us to use LSPs over the different core switches to distribute the load of traffic over them. Again, we wanted to retain our 10 gigabit access switch resilience using the PXCs. So, well, first of all, for MPLS, you need to do, basically you start to make an IP network, which was sort of new for us, well, not entirely, but so we needed to run OSPF. OSPF is quite slow in detecting a failure. You have to wait for the timeout. So BFD came into the picture. The default for the signaling in our labels is RSVP-TE. So we used that. We could also use LDP there. That was not the default. We used RSVP-TE. We defined primary and secondary paths, and we did per VLAN 1 VPLS instance. With all statically defined VPLS peers, so they won't try to find other paths and that kind of things. And these LSPs were load balanced over the multiple switches. Port security was not an option. It didn't work.
And so we had to go to layer 2 ACLs, which are numbered ACLs, so there's only a limited amount of you can use, but it's all still under what we need. For now, we'll enter these things by hand. So this means an operational shift, because port security, you could say, allow a new MAC address to be learned, and that new MAC address was learned, then now people have to come up with a new MAC address up front for us, or they call us in the middle of the night, like, I replaced the router and it doesn't work anymore. So, yeah, how does it work? On the left side, you see, well, the physical setup, a little bit more simplified. So on the top, the member routers connected to this layer 1 patch panel, automated patch panel called photonic switch. 2 switches still, from which we can switch a member router from one to the other. And then that is being fanned out over 4 core switches towards another access switch. Well, the access switches are now called provider edge routers. The core switches are now called P routers. Again, we make multiple paths over the core switches to balance the traffic over. How do we do resilience in the core, in the MPLS, VPLS cloud? Well, we have 4 paths for LSPs. If something breaks, the backup path kicks in, and there is more traffic going over another core switch. This is totally transparent for the access, for the member routers. This takes 50 milliseconds to converge. In case a whole switch breaks down, we use the photonic switch to switch the members over. That's on the right side picture. The right member router is was connected to the right switch, and we switch it completely over to the other switch. This means that, to the other access switch. This means that we can only have one failure, because this means that there will be much more load suddenly going over the left switch. We cannot do that together with a core switch failure on peak traffic. But yeah, you have to set a limit to what you can do on resilience. So this would be a great platform, but how to migrate to this all? We have to do that without any customer impact. So again, this was the situation in June, July. And well, first of all, we had to rewrite our photonic switch control daemon software. Exactly, not completely rewrite it. We had to make sure that it doesn't work on VSRP failures anymore, but on changes in LSP state in the MPLS cloud. The amount of configuration you need to put on a VPLS MPLS switch, especially on the PE routers, is so huge that we could not type that by hand. All the configurations from M6 were mostly grown over the years by new members. We did it all on the CLI, and to type that all in would be a complete disaster. So we made some automation, some configuration generation software to take that out of the XML structure we already had to describe our network. There was another problem, because we would not like to go right away to MPLS, VPLS. We would like to have these 2 networks we have, migrate one network to MPLS, VPLS, and leave the other network on plain Ethernet for the time being, because we know plain Ethernet works. It doesn't scale, but it works. And MPLS, VPLS was new for us. That meant that we could do that easily for the 10 gig access switches, because we had 2 of them, but all the gigabit and 100 megabit customers were on a switch that sold 2 platforms. So we had to basically do something with them, and what we did is we basically treated the whole switch as a 10 gig customer.
To describe that, this network is the same as I draw multiple times before. It's drawn a little bit differently. The black router is a gigabit access switch, which is connected to the red and to the blue network. We want to change the blue network to MPLS, VPLS. And the other network, we still like to have it on plain Ethernet. And yeah, that cannot be on the same access router, on the same gigabit access router. So what we did is we basically treated them as a 10 gig E customer. So all the gigabit customers were suddenly one big 10 gig E customer for us. Then we basically changed the blue network to MPLS, VPLS. We tested this whole network using our traffic generators, and we moved the production traffic over it. We used the PXEs to switch all the traffic to the blue network. We run our new software, and we run this into production for 6 weeks during the summer. And it worked all fine. So, logically, we did the second half after 6 weeks. We again tested the whole functionality of the network and moved everybody over to the red side of the network. So now we have 2 separate MPLS, VPLS networks. So we need to merge these into each other. To do that, we, on a maintenance window, the backbone links, we waited until the traffic on the backbone links was, on all backbone links was less than half, and we basically cut each backbone link in half because it's all aggregates, and we took one half, put it on one side of the network, and the other half put it on the other side of the network, so we now have a full mesh network. All the MPLS, VPLS it's one big MPLS, VPLS network now. So, yeah, we're basically here right now. We did not change the gigabit access switches to MPLS, VPLS yet, because most of the routers, not all, but most of the routers are not migrated yet to hardware that can actually support MPLS, VPLS. But the conclusion is that the traffic over multiple cores, which was the main driver to go to this, really works. It works beautiful. It distributes the traffic beautiful. We think we increased the stability of our platform because we don't need to switch from one network to the other anymore. We can do that now much more fine-grained by if some access port is broken, we can only take the member of this access port and switch it on to another port without having to fail the whole network over. Backbone failures, we already had them, and they were perfectly handled by the resilience in the MPLS cloud. And we hope that Foundry or Brocade will provide us with higher density modules to support further growth. But at least our core switch is quite doubled in size. How did all the operations go further? Well, we experienced some VFD instability. Sometimes the line card CPU, the line processor CPU, is really busy and then forgets about VFD, which results in timeouts. We resolved this by increasing the timers. We encountered a real bug we did not encounter before, and that is when a LSP path goes down and comes up again, it sort of comes up twice, and suddenly you have 2 MPLS paths. This results then in unequal load balancing because there are more paths, so and that goes then over the paths that just failed. This is really a bug and acknowledged by Brocade, and it will be fixed in the next release of it. I think it's already fixed. Another thing is that multicast replication for now goes over the first link of the aggregate of the first LSP.
So that doesn't scale much if we had lots of multicast, but well, multicast is not really used, so it's not really an operational problem at the moment. When you do PIM SM snooping, then it suddenly balances over all the LSPs, but there are some serious bugs in this thing that are more serious than not be able to not be able to scale multicast. And we believe that this will also be fixed. Well, this was a much more a headbreaker. We measure our delays over the platform by using the RIPE TTM boxes. Those are boxes with GPS clocks on two sides. They send a timestamp from one box to the other and measure the delay. And the moment we moved to MPLS VPLS, we saw an enormous amount of jitter with delays up to 40 milliseconds, which is, of course, totally unacceptable. It took a while before we figured out what was going on here. And it has all to do with the attempts from TTM to not overload your network. They send about 2 packets a minute. There's some entropy in it with the source port, so one packet goes over one link, and the next packet might go over the other link. And if it goes over the other link, it needs to do some CAM programming. And the CAM times out in 60 seconds, so the chances that the packet goes over a link that wasn't programmed in the CAM made it that it had to go to the CPU, it had to be programmed in the CAM. That causes some high delays. And sometimes it is in the CAM, so then the packet flows quickly, and you don't see the delay, so that's why you see all the high jitter. We believe that this is not a problem for real traffic, because if you have traffic like that, you might think what you do on an exchange. We are looking into be able to either change the timing of the CAM or disable CAM aging at all. Then we have some members with humor. They sent us a message that their routers are logging that the packets are claustrophobic because they were all packed. They got all packed into these labels on top of it. Now the good stuff. I have to enter the good stuff. This is America. Well, we think that our platform is much more stable than it was because there are way less big changes when we swap over. It works basically it works all fine. The L2 ACLs work much better than port security. It does not affect line card CPU as port security sometimes does. So we're really pleased with this. It's way easier to debug the customer ports because we now can individually swap one port from one Ethernet port to the other Ethernet port. Basically, we finally got some configuration generation, which was a long-term thing we would like to have, and that was now an absolute necessity because of the huge configurations. And we can scale, we think. We can go to, we have much more ports in the core, so we have bigger devices. We have a platform we hope we can grow on, so we hope we can provide the growth we need. There were some issues found, but as I described, not any customer traffic was affected with that. Again, increased platform stability. This is all very nice, and I welcome your questions on this platform. Oh, this was crystal clear.
Thank you, Arian. Next,
Joe.
Yes.
Can we do one question? Or,
Yeah.
Do we have a couple of moments?
Yeah, we
All
have
right.
5 minutes, so
Cool.
if there are questions, please come to the mic.
Cool. So did anything change for your Gigi access customers in terms of providing them more resiliency, or are they still home to one access switch?
Yes, yes, they are. In that sense, nothing changed for them. The ports on the photonic switches have a number of limitations. First of all, they are only working for single mode interfaces. So we can only provide it for single mode. But I think the biggest reason not to do that is because the photonic switch ports are too expensive for the cheaper gigabit ports. And if you see remember my first slide with all the port growth, there is absolutely no growth, and it's even a decline in gigabit ports. We don't do any 100 megabit ports anymore.
Okay.
So we really focus on 10 gig. 100 gig would also go over the photonic switches most probably.
Okay, makes sense. Thanks.
Thank you, Tom. Anyone else? Awesome. Thank you, Aryan.